Thank you. First of all, thank you everyone for attending this lecture despite this little revolution at the entrance of university, you know, this strike. Thank you, Professor Mencucini, for inviting me to CREAF. So today I will speak about work which was conducted by a rather large group of people representing several institutions, University of Albany, where I work, United States Geological Survey, USDA Forest Service, and people from Oregon State University who formed this consulting company, but they like to be part of this company rather than university. The title, as you can see, is newly identified role of the deciduous forest floor in the timing of green up. So I think I should I think my lecture will be self-explanatory in a way, so I don't need outline, but I have to start with some important things, such as what is this forest floor we're dealing with. So we're going away from Mediterranean, we're flying to temperate forest, and this is how spotted soil profile would look like. On the top of this profile, you have three layers called forest floor. They consist of litter layer on the top of floor, which is just you know, fresh or semi-fresh litter. Then there is a fermented layer or fragmented layer, OE, and then finally below them there is a humic horizon, OA, which holds most of the organic carbon for this type of soils, and also it has rather fast turnover time of carbon. It holds most of roots in this type of forest ecosystem, which is deciduous forest. Okay, so the talk about the role of this soil horizon in phenology of deciduous forest. Now, I would like also mention several ecophysiological functions of forest floor, which might explain later our approach and results. First of all, as you all know, forest floor is a shelter for decomposers, insects, earthworms, burrowing organisms, which mechanically help to mix it and, you know, support this rather fast turnover time for carbon there. It's very efficient area for recycling of carbon. More than 90% of all litter above and below ground litter is actually recycled within the forest floor. It's a good retention, it's a good space for nutrient retention. It has a lot of carbon, soil organic carbon with exchange sites, so that's why ions of nutrients, they can be held with quite efficiently by this layer. It's also a good place to retain the water. By the same reason, it has a lot of organic matter, but also it has very low bulk density, so it has a lot of space where water can actually occupy. It controls the evapotranspiration due to capillary action of the same soil organic matter, and it controls soil respiration because this is where the most of organic matter is, and you know, of course, carbon dioxide exchange with the atmosphere. Now, because of this fast recycling of nutrients in forest floor, we're finding a good correlation between chemical composition of forest floor, at least nutrients, basic or important nutrients, and the chemical composition of foliage. Here you can see this relationship for different types of ecosystem from the work Rosato et al. This is like deciduous forest, this is savanna, and this is leaf concentration of phosphorus, and this is soil concentration of phosphorus. This is leaf concentration of calcium, and this is soil concentration of calcium. So forest floor has a very similar chemical composition. It has the concentration of nutrients in forest floor and foliage, they correlated. Another importance of forest floor in ecophysiology of forest is I would call it like a thermal blanket. It protects roots and soil fauna from rapid variations in air temperature, for example, freezing time in spring, won't penetrate deep into the soil, and early frost in the fall also the same story. So protect roots and fauna there. This function is supported by two important physical properties of this forest floor. It has very low thermal conductivity, which at least 10 times lower than, for example, thermal conductivity of snow. And snow, as many people know, is a very good thermal insulator. I know that ecologists know about this, snow manipulation experiments when you move snow from one place to another and see how warming would, change, for example, preservation of roots and so on. So forest floor has lower thermal conductivity. It also has very low thermal diffusivity, which is at least 5 times lower than snow. The difference between, just to remind you, difference between thermal diffusivity and thermal conductivity is that thermal diffusivity, think about this as a ratio between heat which passes through the layer and heat stored within the layer. Technically, you can calculate it if you know thermal conductivity, and then you divide it by density and specific heat. Now, why it's important? Because forest floor is the space, or it's a part of soil profile with a very significant changes in water content. In spring, it could reach easily the saturation field capacity, and in the midsummer, the concentration of moisture there might drop well below 10%. What is important for us, however, is that addition or removal of water from forest floor won't change this property, thermal diffusivity, much. Why? When you add water, thermal conductivity increases, but so density and specific heat. So water has the highest specific heat among all natural, elements on our natural bodies on the surface of our planet. So that's why this ratio stays more or less constant, and it's very low compared to other natural bodies. As a result, if you look at the penetration of heat through the forest floor as diffusion process, you will find, so here is the simple diffusion equation. Here is K is this thermal diffusivity, and smaller the K, slower this wave moves through the forest floor. So the spring thermal wave moves slower through the forest floor than it could move through snow or through mineral soil. That turns to be important for our conversation. Now, which problem we were investigating, or which problem we tried to resolve by this work. There are a number of observations. Here is actually our data for Adirondacks. This is small watershed. It's only about 2 kilometers in size, in diameter, kind of a linear size, about 2 kilometers. On the left slide, you can see, I think it's NDVI values for certain day, 2005. And on the right, you can see the so-called start of the season, or beginning of active growing season, as it defined by satellite, by remote sensing data. And you see that over this small distance, the start of the season for fairly uniform forest ecosystem changes drastically. It could changes quite significantly. The difference could be 10, even 30 days. So the red here is about like 70 day of the year, and the yellow is over 100. So it could be quite significant. Why it is a problem? Well, plant phenologists, they typically think in terms of temperature, other temperature derivatives like degree heating degree days and so on. And they solve this problem in a very simple way. They're just saying that let's say sugar maple, which grows in this area, requires different number of heating degree days than sugar maple, so the same species growing here. And they adjust this, kind of climatic components there. You might say that, guys, here you're showing me it's not the same species exactly. That's the forest ecosystem. Yes, it's deciduous forest, but it consists of number of species. So this problem really exists at different levels. If you look at at the phenology of clones of the same species. So here is the data for Norway spruce clones growing at this International Phenologic Gardens experiment. And for the same, for clones growing at the same mean annual temperature, the difference between clones which put their leaves out first and the latest could reach more than 2 weeks. Again, this is clones. So the problem really exists. Again, the problem is that there is spatial variability of phenology for the same species, even for the same clones. And this variability can be accounted fully by temperature. So are we missing some drivers of spring phenology other than temperature? And this is exactly our point. So traditionally, phenology considered to be a kind of product or response to weather, climate, as well as vegetation, so the species composition, landscape. But recently, some people start arguing that we might be missing, bigger picture here. And this, for example, was conclusion from the work of Josher and others. They say that since flushing of leaves is a target-driven process, and all the influential nutrients are involved in cell extension, membrane function, and stability, it would be reasonable to suggest that our studies, our phenological studies, might overlook the important role of foliar nutrient concentrations as a controls of phenological phases. So foliar concentrations. But few slides before, I showed you that foliar concentrations, they relate to soil. So that's why it makes perfect sense include here additional drivers such as soil. So we'll call them edaphic just to be consistent. So edaphic factors, soil-related factors of phenology. Also, we're living in the time when we have strong global warming. And the time when we still have acidic deposits. Warming changes climate, it influences vegetation. Vegetation and climate, they have influenced soil as well as acidic deposits. So there are a number of interrelated drivers of phenology here. And at this time, of course, there is a strong signal in phenology. So the trees, they move their phenologic phases early. But looking at this picture, you can say that if you look at the geographic distribution of phenologic phases, you really don't know how much in this, changes in phenologic phases was caused just by temperature, how much was caused by landscape features, maybe soil, better say soil, or changes in acidic deposits. There are, I managed to find 3, I think, important papers, but not more than 3 papers on this topic of what's the role of edaphic factors in phenology. The first paper is by Velgalaski, who investigated phenology of trees growing, exactly former agricultural trees like apple trees, peach trees, pear trees, I guess, apple, this is what I remember, growing along the fjords in central Norway on old agricultural soils. What he found in his study is that trees growing on on more acidic soil, so with a lower pH, it seems like they're going to bloom early. He made some number of other observations, but because of the statistical approach he used, he was not able to separate this, factors, some other edaphic factors from climate factors. Dahlgren and others, they operated at a different scale. They investigated phenology of forest herbs at a really small scale, like several hundred meters. So they look at this plots, 2 by 2 meter plots, and they applied basically structural equation modeling to understand if there is any causal connections from phenology to plants. They had about 5,000 individual plants which they investigated, and they were looking for about 16 different variables. For structural equation modeling, you need that your number of cases be at least 10 times more than the number of variables you're looking for. And the first glance, that was a perfect match, 5,000 cases and 16 variables. But then you look at the way they estimated edaphic factors, and it turns out that they sampled soil only in 25 places, 25, and they interpolated properties within this 200 meters, large plot. So there is you cannot call this independent measurements. Finally, but what they found interesting thing that despite all these problems, they found that potassium concentration seems to be affiliated with the early appearance of these herbs than at the places where the potassium concentration was low. But it was also some problem with separating potassium concentration from the impact of actually southern slopes. In other words, southern slopes, in their case, they always had more potassium than other slopes, but their method didn't allow them to separate completely, entirely this potassium from slope exposure. Finally, Arendt and others, they made the control experiment. They just took acclimated clones of European beech and planted them in natural soil of different pH values. Unfortunately for us, they didn't tell how they measure pH, so in water, in salt, and also they didn't measure some other chemical properties such as aluminum and such. And that's very important because at low pH, acidity is regulated by hydrolysis as well as by aluminum. And if you have low enough pH to mobilization of aluminum from soil matrix, you're dealing with a toxic element in your solution. So we don't know if their acidity, their soils were had any substantial amounts of available aluminum. We don't know that. Anyway, the result was that pH, at lower pH, it seems like the tree goes to bloom early, and also at the same time it was the early cessation, so the pH kind of moved them this way, the whole growing season, but the length of growing season didn't change much. So this is the kind of summary of what we knew before our work. So this is the day of the year, this is start of the season. So we know that low pH, at least in two works, was affiliated with the early start of the season, and also southern exposure or high potassium concentration seems to be also contributing to early spring. Our work was conducted in east coast of United States in Adirondack Mountains. So here's New York, here's Montreal. So this is the area which is kind of zoomed here. We used 26 small watersheds, 1 to 4 kilometers in size in the area, and the total area of this polygon is about 150 by 150 kilometers. Vegetation, as I already previously mentioned, is a deciduous forest. Forests consist mostly of sugar maple, and as a matter of fact, that was the original reason for this study. So sugar maple has its important commercial species, especially in northeast of United States, but it also has beech, yellow birch, red maple. It's mature forest, 80 to 150 years old. This species, the combination of this species, as it was shown by Richardson and colleagues, they have statistically similar phenologic phases. So although there are species variability, but according to ground observations on their phenology is very similar, and statistically you cannot distinguish among these different species. We characterized forests first of all with NPP values from remote sensing data. We use moderate resolution imaging spectroradiometer. Here is the specific product which we use. For phenology, we use a different MODIS product, which was done by USGS. We were dealing with so-called surface phenology. It's different from actual phenology you can observe on the ground, where you can see individual trees. From satellites, you can see pixels, and within the pixel, you can have group of trees maybe different combinations of trees. Nevertheless, a number of works, they show that surface phenology correlates well with the actual phenology, with the observations on the ground. However, it is important when you're using surface phenology to be consistent in the definitions which you operate. Start of the season can be estimated by a number of different criteria, and here we use USGS product where they apply consistent greening. So here is the illustration. So here is the seasonal changes in NDVI. It's not from MODIS, but it's, you know, it has more variability, and it shows this concept, I guess, better. Why this point is chosen as a start of the season? Because after this point, NDVI might go up and down, but never below this level. Never below this level. If you choose this point, so you're in trouble because it will go below. It doesn't mean that this is better than that, but to be consistent, we need some criteria which can be used across, you know, across our work. Now, in climate data, we use DAMET data set. It's average, maximum, and minimum monthly temperature and monthly precipitations. We also use digital elevation model and GIS to derive direct and diffused incoming solar radiation on the assumption of 50% cloudness. So it's not really climate data, but it's derived from the digital elevation model. So here you can see what else we use digital elevation models for. We estimated, of course, size of each watershed. It was a separate variable, average elevation, slope, aspect, photo period. Now, for most, soil data, we use bulk density, loss on ignition, pH measured in salt and water, base saturation, and so on and so on, cation exchange capacity. And also we use our variable, it's a categorical variable, we call it acid, A, B, or N. This categorical variable represents overall acidification of soils in watershed. So if base saturation is below about 20%, and this is empirical threshold which we found in a number of studies, it means that if it's below 20%, it means that aluminum already become available. So aluminum was mobilized from soil matrix, and soil water has free aluminum. And if it's above 20%, there is no aluminum, we call it basic, but it's not really basic. And if it's close, plus minus 1% from 20, it's neutral. So that was very important for our study variable. Methods, we use two methods. One is statistical studies, and another was process-based modeling for certain dependencies, which we consider in this work. Statistical analysis consisted of, I would say, 4 steps. First was variable selection. We have so many variables, 60 variables and only 26 cases. So that would, cause a lot of trouble for students who study linear regression, multiple regression. So that's why we have to use some new technique, and we use this VIP, variance importance in projection. This technique is was proposed to solve problems related to which people face in the pharmaceutical industry, for example, when they have a lot of variables and these variables closely correlated to each other. So what this variables importance in projection does, it look at the each individual variable contribution to principal component of the data set. The second step is partial least square regression. We use Nepal's algorithm. This is nonlinear iterative partial least squares algorithm with V-fold cross-validation. So this algorithm allows to transform raw kind of data matrix into principal components and residuals. And the principal components, again, you can use to check how much individual variables, even correlated variables, contribute there. However, you might face the situation when you have 2 variables, both of them contribute, they highly correlated, and you would like to know which of them still is more important than other. So that's why we check all our edaphic variables and climate variables on mediation by other factors. And I'll mention this in a second, how exactly we did that. And at the end, we did Monte Carlo simulations just because we have 26 watersheds, and we want to change average start of season values for these watersheds in the range of kind of natural variability to see if every time we will get the same number of variables in our model. So that was, I think, a necessary step at the end of our analysis. So here you can see results for variable selection. These 10 variables, actually, they all have VIP greater than 1. That's the threshold. If you're interested, I can explain why it's 1. Threshold for these variables. And red bars here, they represent edaphic factors. Green, landscape factors, or, related to landscape. And blue, climatic factors. This model describes 85% of SOS spatial variability, and edaphic factors describe from more than 30% of this variability. The next step, as I mentioned, was test on mediation. So we did use approach proposed by Judd and Kenny for estimates of indirect effect as difference between two regression coefficients. Basically, it's a very simple method, but it allows you to reduce number of variables which are less important than others. First, you establish direct connection. So you see if there is a zero level connection exists between, for example, climate variable and phenology, between landscape variable and phenology, between edaphic factor and phenology. And then you combine this variable in multiple regressions, and you compare the coefficients from this simple regression with the multiple regression. If you see that in multiple regression, coefficient for certain variable become insignificant, it means that this variable is fully mediated by other variable, and so you're leaving only variable which is still significant in multiple regression. If both of them significant, it means that there is a partial mediation, and you can tell, basically more about that. So when we check on mediation, we get rid of several variables, such as spring precipitation, April precipitation, March temperature. They were fully mediated by April temperature. And slope exposure was actually mediated by two variables, by acid, our categorical variable, and by potassium variable. This is our result. Results which represented on this diagram. What you can see from this result is that there are three prominent, it's actually more than three, because we use, acid is a categorical variable, so it has three values. But it's three phenologic variables which contribute to variability and describe about 30–40% from all spatial variability in SOS. And these variables are concentration of exchangeable potassium in soil, acidification of watershed. We found that we found opposite, so to speak. We didn't find any connection to pH. However, what we found is that on a less acidified watersheds, spring comes early, and vice versa. In acidified watershed with very low base saturation, spring comes late. We also found that thickness of forest floor delays the start of the season. So in watersheds where you have thick forest floor, you actually compare to watershed under the same conditions nearby, the start of season will come late. So how to explain this, findings? So here are three hypotheses which we put forward to explain these findings. So first, about potassium. Well, potassium is an important element, and we believe that the watersheds with elevated level of potassium, they have early start of season because potassium works as a regulator of non-structural carbon transport. It helps, and without transferring non-structural carbons into leaves, you won't have start of the season. Second, which is kind of interesting for me, I didn't know that, but I found this reference in literature, and maybe here there are people who can educate me more on this topic, but it seems like potassium also very important for starch synthesis. And in the fall, when the starch accumulation could be done, so starch is important battery for spring, and if there is no starch accumulated, so the spring will come later. That our suggestions why potassium might be important, and why statistics pick up potassium as important variable here. With acid, we think it's more straightforward because, as I already mentioned, our categorical variable separates watersheds where there is a mobilization of aluminum from soil matrix from the watershed where this state is not reached yet. And aluminum is a toxic element. There are a number of papers which shows its negative obstructive impact, especially on fine roots and tree growth. So if you have increased concentration of aluminum, that will slow down the spring on this particular watershed. Finally, our hypothesis about thickness of forest floor. As I mentioned before, forest floor is a blanket, is a thermal blanket. Thicker the blanket, longer it takes for heat wave to reach the to warm up all roots after winter dormancy. However, as one of the reviewers mentioned, so this results they published last year, but as one of the reviewers mentioned, there is a conceptual problem here in our hypothesis about connection between thickness of forest floor and start of the season, because one can argue that there is a negative feedback between start of the season and thickness of forest floor. If season starts early, that theoretically could increase growing season, that might increase NPP, and so that will increase input of litter into forest floor. So forest floor under the same kind of, under the same conditions, under the same rate of degradation, will become thicker. But thicker forest floor, according to our conclusion, delays SOS, and that should propagate to NPP, so it should decrease NPP and it should decrease the OA. I'm not saying that, so we have to address this issue, and I'm not saying that this feedback, this negative feedback doesn't exist. Most likely it exists. But in our particular conditions, what we found is that thickness of forest floor is regulated by organic carbon preservation processes rather than production. We found correlations between thickness of forest floor and, for example, exchangeable acidity. We found the correlation between thickness of forest floor and carbon to nitrogen ratio, which is important parameter which regulates the preservation and the rate, actually turnover rate of soil organic carbon. So that's why we kind of not dismiss this completely hypothesis about possible negative feedback. Perhaps it exists up to some extent and there is an impact, but we didn't find any direct correlations between thickness of forest floor and NPP. So that's why we made another analysis. We made estimates of how much time would it take for spring heat wave to pass through the I would say rather like that, not that, through the forest floor layer of different bulk density and different contents of water and so on. So in winter, as I already said, the surface temperatures, they often drop well below biologic zero in this climate, sometimes even below the freezing point, and in summer they're well above. So in spring, the temperature increases fast at the surface, but then it takes time to warm up forest floor to the so-called biologic temperature at which microbial activity starts kicking in like really fast. So we use the simple thermal diffusion model. Here is solution for delay of certain temperature propagation. You can use it for 5 degree, for 0 degree. The equation looks the same. It's directly proportional to the thickness. and inversely proportional to inversely proportional to the thermal diffusion. So when you do this estimates, this is spring. When you do this estimates, you can plot this. You can vary your thickness of forest floor, and here is this dot lines. They represent two cases: for forest floor which is completely moist, and forest floor which is completely dry. As I mentioned early in my presentation, water cannot dramatically change thermal diffusion, and I guess that's why we don't see like principal difference between these two curves. So it's still showing increase in the delay. So this is delay compared to atmospheric temperature, delay of warming up at the bottom of forest floor compared to atmospheric temperature. And you can see that depending on the thickness of forest floor, it can go up to couple weeks. On average, yes, and the straight lines, that was 95th percentile for our for our Nepal's algorithm, for our multiple regression, partial least square regression model. So there is the overlap between these two models, which shows that on average 1 centimeter of forest floor delays the spring on about from 1 to 1.5 days. Conclusions. Conclusion is that our work points to an additional new role of forest floor as a modulator of the climatic drivers controlling the rate of spring soil warming and the recovery of trees from winter dormancy. So it's a new ecophysiological role of forest floor. This conclusion, of course, is supported by robust statistical analysis as well as by modeling, which I showed you previously. So what's next? What is important? I'm asking myself questions like, so does it mean that all these edaphic factors, they might have some kind of global, or already had a global impact on the rate at which spring comes to northern or southern hemisphere? Can in future edaphic factors actually limit forest response to climate warming? This question is quite reasonable because recently people published papers on which reflect on some delay at the rate at which phenology, at which start of the season comes to northern hemisphere if you normalize this rate to, let's say, 1 degree warming. So before it was 4-5 days per 1 degree warming, but after 1998 to the 2010, it's more like 2.3, 2.7. So there is a delay. Is it because of edaphic factors slowing this down, or as because some people saying that trees, they need not only heating degree days but chilling degree days, and in winter, it's getting warmer. But estimates which I saw before, they cannot fully explain this phenomenon. So thank you very much.
Okay, many thanks, Andrei, for the interesting talk. I like the combination of mixing vegetation properties and soil properties.
I hope I mix them in a proper way, right?
Exactly.
I'm not sure.
Okay, any question?
There's plenty of questions. But well, this is nice that you use this as a clue of the soil organic matter and the soil organic layer as a clue of what's going on with temperature warming. This is nice, yeah, very nice. And I think that maybe you shouldn't need to look for all these other possible factors, but by itself, by being a kind of buffer, maybe through evolution.
Evolution.
Have learned that this is a reliable tool. In fact, we're working on that. We're preparing a paper on that. Yeah, we can talk later.
Okay, yeah, with pleasure, of course. And yes, we're looking into this.
So we agree that is a clue. But the other points that you raise here are also interesting. But for example, we think that maybe you didn't give the importance that it has to photoperiod. You passed by a little bit about photoperiod, but then you provide also potassium. Potassium is a really important nutrient. It's not only because of the reasons that you are telling, but mostly because it's driving and it's controlling the water transport not only the solute transport, but even the water transport. So,
okay.
So this I think this is a good point that you raise. So and what else did you? And then the different statistical analysis we can discuss that too, structural equation modeling or some other possibilities. But the main thing that I want to tell you is that we are delighted to see you.
Thank you.
But we think that you can even go further and try to find additional physiological mechanisms that are related to that. And then that maybe you should take into account also the above ground clocks. Yeah, the photoperiod seems to be very important in addition to chilling.
Yeah, photoperiod is not changing. I see your point. Yes, it's not changing, and
not changing, but it's driving the change of the sensitivity to warming.
It's driving the change of sensitivity to warming. Yes, I can show you a paper where we arguing pretty much about that. But in this particular work, I think the reason why photoperiod didn't show up as important variable, because it was done, the whole period, it's a MODIS observation from 2001 to 2014. So it wasn't really strong warming signal there to perhaps for some other variables to kick in, but photoperiod, yeah, I understand your argument.
So thanks very much for your insightful talk.
Thank you.
Other questions?
You have very strong gradients, I guess, in the topsoil and in the early season, and strong temperature gradients. What is then the relevant temperature for plants or phenology?
Right. Yeah, accidentally I have more slides. So, do I have this? Oh no, I thought too much about myself, too good about myself. But no, I didn't show you this slide. But what we did very simple estimates at first. We just looked. So we have this SOS dates, and we look at what was the temperature at the time of SOS date at the given location. And we found that we found large distribution from literally 0 degree, from freezing point, to almost 20 degrees Celsius. The peak, the maximum, was exactly at the 5 degree, which is biological temperature, the temperature at which microbial activity increase dramatically. When this temperature in soil is reached, it's increased dramatically. That gave us another reason to look into the heat diffusion, because we realized that this isotherm, 5 degree isotherm, is really critical for plants. But again, it's not like, unfortunately, again, I didn't put this slide here, I meant to do that, but it's a distribution. But this distribution has, so it's a distribution, here is temperature, and here is the frequency, and so here is like 0 degrees Celsius, here is 20, 10, so here will be 5. So at 5, we have definitely spike, but then it's like beta distribution moved there. Again, what it is, that's the surface temperature at which start of the season occur. And for us, that was a clue that, look, at some locations, it happens at 5 degrees. But why at some locations it happened at like 15, 20? So the first thing I did, I just look at the thickness of forest floor, because I kind of had this mechanism from the very beginning. And yes, indeed, it was that forest floor thickness increases, this way. And that's why atmospheric temperature have to bypass 5 degrees, and then we have to wait for a certain time till the entire layer will reach this biologic temperature. The 5 degree we call biologic temperature. I don't know, there is literature in US about the importance of this 5 degree, not 0, not 4, but 5 degrees.
So this is the point. We find the same telescope, 5 degree looking at the whole world. Yeah, but then we attribute this to this adaptation through time. So the point is that it's very much strongly linked to thickness of the organic layer?
Yes, this is atmospheric temperature, but because I didn't have soil temperature. My point is that soil temperature, most likely in all these different cases, was 5 degrees, because otherwise, if you don't have microbial activity, you cannot start the season.
No, you are right.
Yeah,
This is what we are seeing in our global analysis.
Mm-hmm. Okay.
But we attribute this to, for example, because it's not in all sites 5 degrees.
Yes.
We attribute this to adaptation throughout evolutionary times, to the conditions of the sites they are living in.
You're smarter. I mean, it sounds more sophisticated. I was when I when I saw that, I thought about that it's just the thickness of layer, maybe.
That's very important, because it opens our eyes. Yeah. And so, sorry, the question was, so you found a relationship with this?
Yes.
Okay.
Yes. Yes. It's
so
there.
The thickness.
Yes, with the thickness. Yeah, that's.
But this also fits, the temperature at the end that they suffer or they are submitted, because the thickness determines the temperature that reaches their roots at the end.
Yes.
Okay.
Yeah. So that's yeah. Mm-hmm.
I suppose if you were to look at sites where the very deep organic layers like PT soils, perhaps there may be a clue there, or comparing them with sites with very shallow.
But
you're supposed to look at this sort of variability here. No?
Well, our variability is from about 2 centimeters to 15, the maximum one. So that's the range of variability. For in order to look into like peats and other type of soils, we will need kind of find new ecosystems so that we will have consistent composition of species, right? So.
Yes, of course.
Yeah.
Okay, any other questions, Mark?
Yeah. You can have wood brick from cutting stems cut and put in water.
Mm-hmm.
So this means that the nutrients and the carbon required for at least to start the growth of new leaves are already there in the stems.
Oh, you mean that, you mean to make control experiment to check this hypothesis, or?
Well, I mean that I don't see, I understand your result, right?
Mm-hmm.
I don't see which is the link between the soil and the buds in the top of the canopy. If when stems have no roots,
mm-hmm.
they can develop without requiring anything from the roots.
Mm-hmm.
This is at the beginning. Once they need water, then I understand that the conduction from the roots to the buds is needed. But at the beginning, which is the start of season, it's hard to find the roots.
Mm-hmm. Yeah, thank you for this question. This represent what we're dealing with is equilibrium state. So it's about, as I mentioned, about average of 14 years of observations. So now imagine if you isolate your tree from forest floor, what will happen? Without nutrients, without recycling, so 95% of all nutrients which vegetation receives, it comes from the recycling. And in equilibrium, it's natural to expect, and I showed this slides where you can see correlation between nutrients in the plants, in the leaves, and nutrients in the soil. So it's equilibrium. I agree with you that if you take, I don't know, the plant and bring it to home, nutrients already, for example, there, so it will put leaves depending on what temperature you have and so on. The point here is that we're talking about equilibrium and long-term equilibrium, basically. So the plant chemical composition is in equilibrium with soil, and we found correlation between soil and SOS and start of the season. I don't know if I explain it. Okay, it's my I see. Well,
trying to find why something happened in the roots can affect the behavior of.
Oh, okay. I have.
If when they are not connected, it happens.
Okay, I think I might have explanation. Let's say we have 2 trees, clones, growing over different soil. One is rich soil, another is not rich soil. And then you cut branches from both of them and brought them to the same, environment. So my question is, which one will put leaves first? According to our work, the one which grew over rich environment, and so it has higher concentration of nutrients within the tree, most likely has more resources, and it will come up earlier. Yeah, we can, again, that's testable. Yeah, I have to test it. I agree with you, yes.
That's a nice experiment to do, yes.
Yeah, but...
Okay.
But it's actually a very good point. Thank you very much, and I think I will... It's relatively easy to do, because we have a range of watersheds, so we already have the... we're actually now using drones and hyperspectral camera to link canopy chemistry with soil. So we can use contrasting locations and make this simple experiment which you suggested. Maybe it will be complete fiasco. I don't know.
Anyway, many thanks for the talk.